The universe is really big. We live in a galaxy, the Milky Way galaxy. There are about 100 billion stars in the Milky Way galaxy. And if you take a camera and you point it at a random part of the sky and you just keep the shutter open, as long as your camera is attached to the Hubble Space Telescope, it will see something like this. Every one of these little blobs is a galaxy roughly the size of our Milky Way, 100 billion stars in each of those blobs. There are approximately 100 billion galaxies in the observable universe. As a cosmologist, I want to ask, why is the universe like this? One big clue we have is that the universe is changing with time. If you looked at one of these galaxies and measured its velocity, it would be moving away from you. And if you look at a galaxy even further away, it would be moving away faster. So we say the universe is expanding. In 1998, we learned something crucial about the universe that we didn't know before. We learned that it's accelerating. The universe is not only expanding. If you look at that galaxy, it's moving away. If you come back a billion years later and look at it again, it will be moving away faster. Individual galaxies are speeding away from us faster and faster, so we say the universe is accelerating. Unlike the low entropy of the early universe, even though we don't know the answer for this, we at least have a good theory that can explain it if that theory is right, and that's the theory of dark energy. It's just the idea that empty space itself has energy. In every little cubic centimeter of space, whether or not there's stuff, whether or not there's particles, matter, radiation, or whatever, there is still energy even in the space itself. And this energy, according to Einstein, exerts a push on the universe. It is a perpetual impulse that pushes galaxies apart from each other. Because dark energy, unlike matter or radiation, does not dilute away as the universe expands. The amount of energy in each cubic centimeter remains the same even as the universe gets bigger and bigger.
We're going to talk about the mass effect fields now, and also dark energy, and is it feasible to think of it actually being applied in this universe?
Dark energy and dark matter represent the cutting edge of science. In fact, that's what I work on professionally. I work on something called string theory. We think we're the lowest vibration of tiny little strings, but the next vibration could be dark energy and dark matter. In this room, for example, the Earth moves in a wind of dark matter, so there should be dark matter right here. We physicists have not yet found it, but we hope to create it with the Large Hadron Collider outside Geneva, Switzerland. The machine is 17 miles in circumference. We're going to slam protons at energies not seen since the instant of Genesis itself, and we hope to create higher vibrations of the string, including dark matter. Dark energy is even more fantastic. It's intergalactic. It's what makes the universe accelerate in its expansion. So dark energy is basically the energy of nothing itself. The universe is made out of atoms. Wrong. We now know that 73% of the universe is made out of dark energy, the energy of nothing that pushes the galaxies apart. 23% is made out of dark matter, which we hope to create with the Large Hadron Collider. 23% of the universe is made out of stars, hydrogen, helium, and we humans, we make up 0.03% of the known universe. So we're the oddballs, we're the backwash. Most of the universe is dark.